Hello and welcome. My name is Robert Perrons. I'm an associate professor here at QUT, and I'm honored to be connected to all three of the organizations that are sponsoring today's event. And specifically, those are the Gates Cambridge Scholarship and two departments within QUT, specifically the Science and Engineering faculty and the Institute for Future Environments. Our speaker today was born in Montana in the United States. He eventually emigrated to Australia, and now he's a naturalized Australian citizen. What you don't see on the slide behind me here is that as a kid, he wanted to be a meteorologist. And Professor Schmidt, don't take this the wrong way, but I think that everybody in this room is quietly thrilled and delighted that you did not succeed more as a meteorologist, sir. And the reason that we are so happy that that didn't work out for you is because what came next on this alternative path was so amazing that we're all the richer for it. Culminating, of course, in you jointly being awarded the 2011 Nobel Prize in Physics. Please, ladies and gentlemen, help me welcome to the stage Nobel Laureate and Professor Brian Schmidt.
Thank you, everyone, for coming out on this lovely Brisbane morning. It is a great pleasure to be able to tell you a bit about the story about cosmology and my part of it, which was helping discover cosmic acceleration. Now, to understand cosmic acceleration, you're really going to have to understand the universe. And I'm going to take you through our history of understanding the universe, because science is really built on the legacy of previous generations, and that becomes crystal clear in cosmology. Cosmology is, in some sense, the biggest scales of the universe, but it's also some of the cleanest and nicest physics and understanding of how science works in the universe, since it is really the science that dates back to many, many thousands of years ago. Everyone has looked up in the sky and tried to figure out our place in the universe. So let's start, as we do this, hopefully, with just a brief thought about our place in the universe. The scale of the universe is huge. This is our Milky Way galaxy. This is what we see when we look up in the sky each night, probably not so easily from Brisbane. There's too many lights out there. But if you look out, this is an actual picture taken from two telescopes, one in the northern hemisphere, one in the southern hemisphere. And it shows the 100 billion stars that make up our own little part of the universe. And when you look up, you can see across this vast distance of about 100,000 light years. And 100,000 light years is the way we describe distances because it allows us to get our head around the vast distances a little easier than the number of kilometers, about 10 to the 18 kilometers. That's one with 18 zeros behind it. That's a lot of kilometers, and it doesn't mean anything to me, doesn't mean anything to you. But 100,000 light years is something I can get my head around. How long it takes light to travel that distance. And so each of you are nanoseconds away from me as light travels. But when you get out into the expanses of space, those add up to time, which goes, in this case, before, essentially before Homo sapiens as we currently know started. Well, about the time we started exponentially growing and inhabiting the Earth, to distances, as I'll show you, that go well beyond. Now, in this little picture, let's put a little picture of the moon up there to give you a size scale. We're going to zoom in on the moon, and we're going to take the deepest picture we can of the universe with the Hubble Space Telescope, where we literally have the Hubble Space Telescope stare at a piece of sky for a couple months, and it's about that big. That's about what the Hubble Space Telescope can see at one time. We're going to zoom in on that, and that's what we see. That is the deepest picture we have of the universe. It shows about 20,000 galaxies in a piece of sky which is 1/13,000,000th of the entire sky. So we think about what that means. How many stars? Well, I got 13 million pictures like that one. Each one has about 20,000 galaxies. So if I look out and I take the Hubble Space Telescope, and I make a lot of them, they're $2 or $3 billion each, so it may take a little while. I have about 260 billion galaxies like our own Milky Way. Each one of those has roughly 100 billion stars each, and we end up with the fact that there are a lot of stars out there in the visible universe. So many stars that we have to think, well, how many stars are there? Well, we can compare it to, for example, the number of grains of sand there are on Earth. That turns out to be a very controversial number. We haven't figured out to about a factor of 1,000. So we actually know how many galaxies and how many stars there are in the universe far more precisely than we know how many grains of sand there are on Earth. But there are more stars in the universe than there are grains of sand on the Earth by several orders of magnitude, maybe 3 to 6 orders of magnitude. Now you might be thinking, but what happens if the universe is infinite? I'm really actually talking about the part of the universe we can see, because it turns out we're in the process of building a new generation of even larger telescopes. And these larger telescopes will allow us to see further. And when we see further, it turns out we see older, but we don't see too many more stars and galaxies. And that's because if we make the most distant image of the universe, we look back 13.8 billion years, and what we see is this image. This image is known as the cosmic microwave background, and it shows a universe not full of stars and not full of galaxies, but rather little ripples of sound waves, hundreds of thousands of light years long, as it turns out, and a universe which is hot, 3,000 degrees Celsius, glowing like the sun. And the reason the universe looks like this is because at this time, the universe is 380,000 years old. The universe is not infinite in terms of time. It has a beginning, which we call the Big Bang. And so no matter what we do, we aren't going to look past the Big Bang, because literally there is nothing to look past. So space may be infinite, but time is certainly not. And so we can only see a sphere around us of how far light can travel in 13.8 billion years. Dream about that tonight. It hurts a little bit, but you can sort of get a sense of it. So let's talk about the beginnings of cosmology. History in science is incredibly important. We do not teach it enough. The philosophy of science is incredibly important because we are humans, and the science we do is ultimately something that humanity is doing for better or worse. And I find it remarkable what humanity is able to do, but to understand what we are able to do, you have to understand the failings of humans. Because scientists are humans, and we come in all shapes and sizes, as any of my colleagues and your colleagues will represent to you. So cosmology, modern cosmology, where we really started applying the principles of physics to the universe, started in 1916 when we were able to start taking the light of stars, spreading them out into spectra, into the colors of the rainbow, and looking, when you look at the sun, you see all sorts of things. For example, helium gets its name from helios, the Greek word for the sun, because helium was discovered on the sun through its spectrum before it was discovered on Earth. So, of course, we have a very powerful diagnostic tool. I can go through in the sun, and I can see how much uranium there is in the sun, 1 part in 10 to the 12 or 13. But I can do that because this is such a powerful diagnostic tool. Vesto Melvin Slipher, someone who almost none of you will have heard of, and I have to admit I had not heard of him when his family gave me a scholarship to study at the University of Arizona. Back in 1986, I believe I received that scholarship. He was the first person to go out and really look at galaxies. Now, we didn't know what a galaxy was in 1916 when he did this work, but he could see that they looked a lot like a star. They seemed to be made up of the same elements of a star. But there was a difference. And the difference was the light was stretched compared to the star. But there was a physical law known as the Doppler shift that he could use to understand that stretch. So the Doppler shift affects anything where an object is moving relative to the wave that it emits. If it's a sound wave, it's a pitch. If a police car is coming towards you, the pitch is raised. As it recedes, the pitch is lowered because the motion stretches the sound waves in one direction and compresses them in the other direction. Light, of course, also is a wave. So if a galaxy is moving away from you, its light will be stretched. This is the miraculous effect that they used to identify that the Malaysian Airlines flight had taken the southward trajectory relative to the satellite. They could see the Doppler shift on that radio waves that it was emitting. So Slipher was able to use this effect to realize that all of the galaxies in the universe seemed to be moving away from us. There was a couple that weren't, but almost all that he saw were moving away from us. And this was a mystery in 1916, because why would we live in a special place in the universe? Since the adoption of the Copernican principle, the idea we should not be a special place in the universe. We should be like all other observers in the universe. This seemed to violate that principle because we seemed to be the center of something where everything was trying to get away from. And that was a conundrum in 1916. At the exact same time, on the other side of the planet, Albert Einstein was formulating his theory of gravity. In 1907, he had what he described as his greatest thought, a very subtle thought. This is 2 years after E equals mc squared. His thought was, I think that acceleration due to motion and acceleration due to gravity must always be equivalent. There's no way to disentangle them and make them different. That's a very subtle thought. So imagine I'm in a box. I don't know where I'm at. I may be here, or I might be in a rocket ship being accelerated at 9.8 meters per second squared. Or perhaps I'm just in a box on the stage being accelerated by the Earth's gravity by 9.8 meters per second squared. He posited that there was no experiment you could do to disentangle those two forms of acceleration, because they were always exactly the same. All right, well, it turns out it took him 8.5 years to solve what that really meant for the laws of physics. And that was the birth of his theory of general relativity, which predicted that space had to be curved and was eventually shown in 1919 to be correct by looking at the sun during an eclipse, and this is actual data from 1919, and you look at the stars, in this case out of focus, but useful enough, and you looked at those stars when the sun was in front of them. The sun would distort space and bend it, and then cause light to be in slightly different places. Then later on, when the sun was gone and it was nighttime, and you could look at those same stars. And that experiment vindicated Einstein's new theory that he had dreamt up for no reason other than it seemed to him it must be true. That idea, equivalence of acceleration and gravity. And it allowed Einstein then to do things that Newton could never do with his theory of gravity. How would gravity work at a universe that goes on and on? Turns out there's no sensible solution within Newtonian mechanics to do that. When Einstein did that, he got a nasty surprise. His solution showed that the universe should be in motion. This all happened in 1917. Now, in 1917, what a universe in motion meant, well, it just didn't make sense. We didn't have the notion of an expanding universe. And Einstein did not know about Slipher's work and would not have even identified Slipher's work, as it turns out, to mean anything in context with his work. So he did what all theorists do when they have a beautiful theory they're sure is right that does not fit the observations. He invented a fudge factor, which he called the cosmological constant. This fudge factor, it turns out you could easily add it to his equations without really changing them. and it's effectively energy that is part of the fabric of space itself. So people always like to ask, what is space? I always say space is the scaffold where things happen. Time is the metronome at the rate that things happen. But this notion said that space is something more than just a place things happen. It also has an energy. And it turns out if space does have an energy, it has a consequence. That energy makes gravity repulsive. And so space will naturally want to push on itself if this energy exists. The more the energy, the more it wants to push on itself. So how did we reconcile Einstein's fudge factor? Well, we went out and we started measuring distances. We measured distances by the way things appear because, of course, we can't lay a ruler down given the vast scale of space. So the further away an object looks, further away an object is, the fainter its stars or its light bulbs or its candles appear. And so one can judge distances by how faint things are. It's a little crude, but it turns out it's based on a very secure law. The main problem is you have to know what you're looking at is the same brightness at all distances. That is, if I look at a star in one galaxy, I have to be confident it's the same number of watts as the star in another galaxy. And Edwin Hubble was the person who went out, and he had access to the largest telescope in the world at the time, the 100-inch telescope at Mount Wilson. You can still see it. It's not actively used for science anymore. And he went out and said, I'm going to look at the brightest star in a galaxy, and I'm going to try to compare its brightness to the brightest star in another galaxy, and I'm going to judge the relative distances of those by the relative brightnesses. And when he did that, he found something quite profound. He found that the faster a galaxy was moving, the fainter its stars. In other words, the further the object, the faster it was moving. He plotted his data in 1929, and I think it's always important to show that crummy little diagrams like this are ultimately what science is all about, and they provide the basis of the profound understanding that humanity has on the world around us. So here, the further away an object is, the faster it's moving. And from that, he announced to the world in 1929, this means that the universe is expanding. Now, why did he say that? Well, I'm going to do a little cartoon and give you some insight. Here's a universe which I can play God and I can expand. And now I want to look at before and after and see what I see. So I'm going to overlay before and after. Well, I've expanded the universe and I see nearby objects have moved a little bit and distant objects have moved a lot. If I were measuring their velocities, nearby objects will have a low velocity, distant objects will have a high velocity. And it doesn't matter where in the universe I am, I see the same thing. We don't live a special place in the universe if the universe is expanding, and we see what Hubble saw. The further an object is, the faster it will be moving away. Now, salesmanship is important. Edwin Hubble has a very expensive telescope named after him and Hubble's law. Georges Lemaitre, a Belgian monk who received his PhD in 1927, entitled, more or less, Here's the Expanding Universe with General Relativity, made the mistake of, instead of publishing in the New York Times, of showing Albert Einstein his work in 1927. In that, Lemaitre showed how Einstein's theory of general relativity predicted an expanding universe, and he showed how Hubble's data vindicated that prediction. Einstein's response to Lemaitre was, your mathematics is correct, but your understanding of physics is abominable. Einstein could not visualize what the expanding universe meant. Of course, Lemaitre is someone who almost none of you will know unless you're in physics. Salesmanship is important. Edwin Hubble is famous, Lemaitre is not. But Lemaitre actually got there first. But Hubble is the person who convinced the world it was true. In 1931, Georges Lemaitre also predicted the notion of the Big Bang, which I'll talk about in a second. So the reason why Hubble ultimately gets credit is because he made it believable for people. Research works when ideas meet reality. It's one thing to have an idea like Einstein had. It's another to believe it. And the way you believe it is through testing ideas. Einstein's theory made a number of tests, which over the last 100 years we have tested and tested and tested, and they've always come true. And the beautiful thing of believability, and this is what makes science useful, is believability allows extrapolation to other domains to allow further testing, but also to use those ideas to do useful things in society. And we should always remember testing should never stop. That's a fundamental tenet of science, is you do not take anything to be sacred. Everything is debatable. So, what did Georges Lemaitre think of in 1931? He said, well, if my universe is expanding, let's put it in reverse. What happens? Things get closer, closer, and closer, and it's almost impossible to imagine how we're not going to end up with something like a Big Bang, that time when everything in the universe is on top of everything else. It is a natural consequence of a universe that's expanding. He called it the primeval atom. Now you can think about this graphically. I can talk about how far two galaxies are apart, and I run the universe in reverse through that dotted line, and I can figure out the time of the Big Bang by seeing how steep that dotted line is. We call that the Hubble constant, or the expansion rate of the universe right now. Now, of course, the universe turns out it's a little more complicated than that, because the universe has stuff in it. Gravity attracts, and so all the stuff in the universe will attract all the other stuff in the universe. And so a universe which has a lot of gravity in it will slow down over time. And so you could have a universe that has a different trajectory depending on exactly how much stuff is in that universe. And this has ramifications for the future. If I have a universe which doesn't have much stuff in it, the expansion will continue unabated into the future. The universe will go on forever and be infinite into the future. Eventually in this universe, I will see infinitely far because I have infinite amount of time to see. And the universe will be revealed. Infinity meets infinity. On the other hand, a universe which is slowing down because it has a lot of stuff in it, well, it has a different feature. If I have enough stuff, just like a ball that I throw up in this room will have less than the escape velocity for Earth, unless I can throw it at many tens of thousands of kilometers per hour. The universe, if it has enough stuff, will ensure it doesn't have escape velocity. The universe will reach a maximum size, come to a halt, like the ball I throw up in the air comes to a halt, and then come back down to ground, or in this case, end not in a Big Bang, but in a Ginab-Gib. That's the Big Bang backwards. All right. So, where do I come in? This is about where I start coming in. Well, let me do one more thing I forgot about. The slowing down of the universe tells us how old we think the universe is from that expansion rate. It tells us the ultimate fate of the universe. Will it exist forever or die? And it turns out it tells us the shape and weight of the universe. And that's because Einstein's theory of gravity says the universe can be curved. So a heavy universe, one that eventually stops and goes in reverse and is finite in time, turns out also finite in space, because three-dimensional space bends around in a fourth dimension onto itself. Now, understanding that fourth dimension is not easy. I cannot visualize it in my head, and indeed, I have never met a sane person who can. You do not want to be one of the people who can. So a heavy universe bends around on itself. It turns out if you put a triangle in that space, its angles add up to more than 180 degrees, just like triangles here on Earth add up to more than 180 degrees. Now, if you're thinking, triangles add up to more than 180 degrees here on Earth? Well, if you're locally, this part of the world is flat, but get a globe out, use a piece of string, tie it into a loop, and make a triangle, and then look at the angles on that triangle, and you'll see they do add up to more than 180 degrees. If the universe is light, it bends away from itself in the shape of a hyperbola. Here, triangles add up to less than 180 degrees. And finally, we have the just right universe, where triangles add up to 180 degrees. And it's just right because this universe is precariously balanced between the finite and the infinite. It's also just right because theorists who like to understand the time right after the Big Bang predict that the universe should have this shape. So, when I was young, I had to choose a research topic. And for those, this goes no matter how old you are, when you're going to do something, you want it to be interesting to you, especially in research. Sometimes you have to make compromises and do something you don't like, but you should always start off trying to figure out how to do something that's profoundly interesting to you. But you also have to ask, can I make other people excited by it? When I'm telling my students, I said, can you make your grandmother excited about what you're working on? And if the answer is no, then you're either working on the wrong thing or you haven't thought about it enough. And the other question is, can you do it? Do you have the skills and resources to do it? Those are the key things. So I grew up in the mountains of Montana. Here I am, I think when I was 6, with my dad, who was a biologist. Our first dog, Scooby. We moved to Alaska, and here I am wandering around, it turns out with a telescope in the mountains just outside of Denali when I was 13. I wasn't using the telescope to look at stars, because it doesn't get dark in Alaska this time of year. There's no snow on the ground. Rather, I was using it to take photographs of moose, grizzly bears, and Dall sheep. But I had a pretty normal life, like most of us. And when I finished, as we heard, when I was growing up, I wanted to be a meteorologist. So I had the opportunity to go out and work at the Anchorage Forecast Office of the National Weather Service. And at the end of that, I suddenly, after thinking I was going to do this for 15 years of my life, realized it wasn't quite what I expected, and I had to reevaluate what I was doing. So I chose to do something I'd be willing to do for free, astronomy. I had no expectation of ever becoming an astronomer, but I knew at least by doing something I enjoyed, I would get the skills that I needed to be successful doing something in life. And I think I was quite ahead of my time when I think of it when I was 16 or 17 at that time, because I still believe that's exactly how people should choose what they do in life. Give it your best shot, get the skills, and skills are the things you need when you graduate, but also 30 years later, as the world changes, you need to have the skills that allow you to do things. And science is a great place to get those skills. It's really future-proofing your life if you do science. So I went off after an undergraduate degree to Harvard, and I thought, wouldn't it be cool to measure how fast the universe is expanding and try to do that accurately so I know how old the universe is? So here I am, 3 years, 11 months, and 4 days after commencing my studies at Harvard, but I didn't count the days, showing my PhD supervisor how fast the universe was expanding, and the answer that I got was that the universe was roughly 14 billion years old. But as we've already seen, that line is straight. And for a perfectly reasonable amount of stuff in the universe, one could imagine that the universe was only 10 billion years old. Now, we didn't really know how much stuff there was in the universe, and so all things were possible, but we did know that the ages of the oldest stars were greater than 12 billion years old. So there was a potential problem that the universe might be younger than the stars in it. And we astronomers aren't too fussy, but that would be bad. So I finished my PhD. My wife, who's an Australian I met, who was doing her PhD at Harvard in economics, we had to solve the dual career problem, which is we made a decision when we got married that we wanted to actually live in the same place. Not a big deal, but it turns out to be harder than you might think sometimes. So after applying to jobs around the world, we both got jobs in Canberra, and we immigrated to Australia, much to my wife's delight, at the end of 1994. And for me, it was great because Mount Stromlo Observatory is considered to be a top 10 institution in the world, and was not, in any sense of the term, a step down from Harvard, which has a very strong department as well. And so the idea was, let's look back in time and see what the universe's expansion was, not just now, but billions of years ago, by looking at objects which are so far away and measuring their distances and how much space has stretched, to gauge how the Hubble constant, the rate the universe is expanding now, has changed, and thereby weigh the universe. And so you can imagine an experiment. If I measure how fast the universe is expanding over time, if the universe has almost nothing in it, its expansion rate won't change back in time. And so if the universe has a trajectory of this line, it means the universe is effectively empty and is infinite. It's infinite in time, and it's infinite in space. On the other hand, there is this critical line where the universe eventually stops expanding and goes in reverse. That trajectory, if you're on this side of that trajectory, gravity is going to eventually win over the expansion of the universe. The universe is finite, both in time and in space. This side of this trajectory, gravity loses, the universe is light, and the universe is infinite. So how could I do this? Well, in everyone's career, you get chances to do things, and in my case, this happened right before moving to Australia. Opportunity knocked. There was an opportunity, and this was caused by changing times in the form of changing technology and changing knowledge. And so the changing knowledge came from a group that I was working with in Chile that had gone out and started measuring a new type, or not a new, but a type of supernova we call type 1a supernovae. What is a type 1a supernova? Well, let's look at the life of the star like the sun. Our sun, in about 5 billion years, is going to puff up and destroy the Earth, I'm afraid, and then eventually collapse down to a tiny little star called a white dwarf. White dwarf's about the size of the Earth, but the mass of the sun. Now, if our sun was instead born not as a single star, but as two stars, that same process more or less happens. The first star that's a little bigger than the second star puffs up and ends up liking to donate a bunch of material to the smaller star. And so as that material gets donated, the smaller star will get a bunch of extra fuel. It will change a bit, become more massive, and that first star will eventually run out of material and collapse down to a white dwarf in a very similar process to what our sun does. When this happens, these objects produce beautiful objects we call planetary nebulae. They're some of the most spectacular objects in the sky, and our sun will eventually do that. Now later on, that first star that got all this extra material is eventually going to run out of nuclear fuel in its center and want to rearrange its nuclear reaction. And when it does that, it'll start donating material to that white dwarf and making that white dwarf heavier and heavier and heavier. And it turns out when it reaches 1.4 times the mass of our sun, it turns out that that whole thing explodes as a giant thermonuclear bomb because the force of gravity exceeds the force of the electrons being able to keep the star from collapsing to a black hole. So the star tries to collapse to a black hole, but it's full of all this nuclear fuel, and that is essentially a blasting cap that causes, in a period of about a second, 1.4 solar masses of material to turn into a giant nuclear bomb. Most of that material is converted to iron, and indeed most of the iron that we have here on Earth and we're exporting to China is formed in these explosions that occur. They're about 5 billion times brighter than our sun, so they're tremendous. And that brightness means we can see them across the universe. So the guys in Chile, and Mario Hamui, one of my colleagues at the time, came up in 1994, and he showed me his diagram of how fast the universe is expanding in the nearby universe. And I noticed immediately that his points were all perfectly on that line, where my points from my thesis were scattered about. So I was rather glad that I had already turned my thesis in, because he had a method that was a lot better than mine at measuring distances. So that was one thing that happened. The other thing that happened in 1994 is the new generation of telescopes, 10-meter telescopes in the form of the Keck telescopes, came online. We had never had a telescope big enough for us to reliably see and measure, for example, the stretching of space to a distant object before. These telescopes allowed us to do that for the first time. And they were helped by new technology in the form of giant digital detectors. In 1994, we had delivered our first 4-megapixel CCD cameras that allowed us to look at enough space to see these exploding stars, which turn out to be very, very rare. The last one seen in our own galaxy was in 1604, and it was seen by Kepler, Johannes Kepler, and Galileo. So you need to actually look at hundreds of thousands of galaxies to find one of these. And so this comes to the point of, why do we do research? Well, we do research ultimately because it's useful. Actually, we do research because it's interesting. The reason the government pays us to do research is because it's useful. And so people say, but what do you do that's useful? Well, okay, what do I do as useful? I don't know. But my field, through this person who at CERN, doing things as mundane as helping people within the CERN collaboration collaborate, invented the World Wide Web, which is about $1 trillion industry per year, compared to the $8 billion invested in CERN. In Australia, we have John O'Sullivan, who used radio astronomy to help invent Wi-Fi. So ultimately, the ideas of basic research percolate up in mysterious ways that you cannot predict. So when the science minister, or lack thereof, comes and tells me, okay, that's great, what are you going to do next? The answer is, I don't know. That's the whole point. The reason why government invests in basic research is because we don't know what we're going to invest, or we're going to invent, and therefore industry cannot do it. This is a fundamental role of government. And if you don't do this, we know what happens. We did an experiment of society. We call it the Dark Ages. I'm not advocating we do that again. And the beautiful thing is research and innovation feed off each other. The techniques and equipment from basic research, for example, digital detectors, which were invented in the US military but were broadly used by astronomers, now percolate into our daily lives. That makes them really cheap for me to use and means I have a $268 million pixel detector that didn't cost me $268 million like it would have 15 years ago, but much cheaper. And I can use that technology that we helped invent and which we all use as society. World Wide Web is another example, and I can list example after example. Pretty much everything that we use today is based on the basic research of the last 150, 250 years, one way or another. Now, as a researcher, you need to take your opportunities when they're handed to you. This is something from Google. Google, I got to visit last year. It's an amazing place. And they have a model which is to fail often but fail quickly. And so as researchers, we do need to fail. We need to make mistakes. But the key of being successful in research is to realize the risky thing you're doing now isn't going to pan out and move to the next one as fast as you can. So we should relish failure. And so for people thinking about their career, it's okay to change directions when a great opportunity comes your way. And in my case, when I realized in a period of 2 to 3 weeks I had an opportunity to measure the future of the universe, I stopped what I was working on. I had 3 papers which have never been written. And I took a huge risk. But that's the purpose of doing research. And remember, failure is an option. So it turns out I wasn't the only one with this idea. There was another team at Berkeley, and we had a very spirited competition to measure the past history of the expansion of the universe. And my job was to take this opportunity and to convince a bunch of senior colleagues around the world, when I was 27 years old, to join this endeavor because I couldn't do it on my own. It was too big. And so you might ask yourself, why would a bunch of senior colleagues, all of them older than me, allow a 27-year-old postdoc in Australia to lead a collaboration of this scale? And I honestly don't know. I had a unique skill set at the time. I was young, and I had all the modern computer skills that I needed, and most of my older colleagues didn't. I had a lot of enthusiasm. One of the things I've realized is I still have a lot of enthusiasm, but I don't nearly have as much as I did when I was 27. But ultimately, I was in the right time, the right place, and I had a great bunch of people who I worked with who supported a young person and just really wanted to get on to the science, and they didn't really care who led it. So my job was to figure out how to discover these extremely rare exploding stars. Here's an image that we would take. There's a couple thousand galaxies in that image. And we would take about 1,000 of these images a night. So that's, in this case, this is an 8-megapixel image that we got in 1996. And the hard part is that because we were taking 1,000 of these a night, we would have roughly 50 gigabytes of data to plow through back in an era when we had Pentium 100 machines, which for those of you who remember were not fast, much slower than my iPhone, with hard drives which were 1 gigabyte. Now, I did not have a supercomputer. I had to figure out how to take literally every computer on the mountain in the big observatory in Chile and daisy chain them together to work on this. And it was a challenge. And to show you what you would look for, you would find an object like this. And the reason we knew that was an object is because we had comparing before and after. So here, nothing has become something in those 24 days. So I ended up having to write image manipulation software which would align these images up to a very precise level, effectively subtract them, and look for the differences. And in 50 gigabytes of data, that turns out to be hard, and my software was barely adequate. And to give you a sense, I take you to Chile, to the Cerro 4 meter, where as the sun sets, we see silhouetted Greg Aldering from our opposition team. We were both using this facility because it was the only one that had one of these big CCD cameras on it that we could use. So astronomers share their facilities worldwide, and it's a great part of how astronomy works. Now, we get 6 nights of telescope time a year. So every second is precious. So as the data comes in, my software is going through and running on it on this morass of computers, and it finds supernovae, but it also finds a lot more junk in the form of asteroids, glitches, variable stars that we have to sift through as a big sweatshop of people, essentially going through and trying to figure out what's going on. Time is of the essence because 18 hours later, on the other side of the planet at the Keck telescopes in Hawaii, we have one of our 3 or 4 nights for the year to get redshifts for these objects and to make sure what we find really is a supernova. So there we have Adam Rees, who I won the Nobel Prize with, and Saul Perlmutter from the other team, because again, he needs this facility as well. It's the only one in the world capable of doing this work. So a spirited competition, but one after about 3.5 years revealed a surprising result. So, as a leader of this team, it was a very flat structure. It was an inverted structure. I was with Adam Rees. We were the 2 youngest people on the team. But we also have to remember that no matter where you are in life, everyone is a leader and everyone is a follower. I got to meet Barack Obama, and one thing I realized is, yes, he may be the leader of the free world, but he doesn't get to choose, for example, his security arrangements. He has to follow what they say. He also follows very carefully what his wife says, as I found out. Always good for everyone. You should always remember that leadership's a 360-degree circle, and everyone needs to take the lead and lead from the people above them, below them, and at their level. That's how you work well collaboratively. I've met generals, and there are generals who definitely like to work down the hierarchy, but a lot of generals don't work that way either. They work collaboratively. And how you do it depends on the people involved, and I would say is an art form. But my basic strategy is to look into the mind of your colleagues and see the world from their point of view and try to do something that's going to make sense to you and to them. And if you do that, normally you're doing the right thing. So 3.5 years later, here is our experiment's results. Each supernova is a measurement of the expansion rate of the universe. We are looking back in time. This is how much light stretched. This is how many billions of years we're looking back in time. And each measurement has an uncertainty. So this is what we call 1 sigma. So that's 68.3% of the time, 2 out of 3 times the correct answer lies from here to here. So you have to sort of use a statistical way of looking at the data, or in your mind, you're going to do an average with your mind. So if I look at the nearby objects, I can see, I can't really tell if on average they lie here, here, or here. But when I look at those distant objects, which I did at the end of 1997 with Adam Rees, I saw that there was a surprise. A surprise, from my perspective, a little bit disappointing, that not a single one of those objects lie down in this part of the diagram. I always liked the idea of a universe that had a beginning and an end. Seemed to make sense to me. Unfortunately, as we find in science, the universe does what the universe does and doesn't really care about what you think. And so our job is to actually measure and figure out what the universe is doing, whether or not you're a biologist or an astronomer, that's always true, and not prejudge the universe. But I also noticed that on average, those objects did not lie in the yellow part of the diagram. Rather, they lie in the top part of the diagram. And when we statistically analyzed, we realized that we were 99.95% sure these objects lie up here and not down there. Now, people often ask, did we have a eureka moment? The answer is Adam Rees and I were working on this, and I just thought we had made a mistake. So we spent many, many months redoing each other's calculations from square one. And at the end of that process, we realized that actually, no, it seemed to be an answer we could not find a mistake. And so it is our job as scientists to tell people what you see, even if you don't like the answer. So it turns out the other team was having the same problem as us. We didn't know about their work, they didn't know about our work, but we both arrived to the same conclusion. And that's why competition can be very good. We had to do this experiment faster, I would say cheaper than them. They had a lot more money than we did. But we also knew that if we made any mistake, this other team was going to point it out to the world at our expense. And in the end, when we got a crazy result, we could self-verify each other's work independently. And the world took notice, partially because it was a crazy result, but also this is the first time the two teams had actually agreed on anything in public. And so when that happens, people were like, geez, what's going on here? So it is for that reason that our team won the Nobel Prize in Physics, and here we are, the 19 of us, all together for the first and only time. We had all known each other, we had all worked individually with each other, but we had never been together as a group. That is the power of the internet. And the internet was not good back then, but it's a lot better now. Now, for those of you realizing that there are no women there, you are right. Astronomy, especially 25 years ago, was incredibly blokey. It's still blokey, but not as bad as it used to be. And it is something that I am proud to say we are addressing in our field and will continue to address, because certainly half of the prospective astronomers out there are women, and it's a matter of ensuring that our field eventually, that would be half women. The other team, fortunately, did have a few women, but they were in Stockholm as well celebrating, and it was a great honor and privilege to be part of what is ultimately not meant to be a celebration of individual achievements. It's a celebration of science. The Nobel Prizes are a way for us to celebrate on an international stage what science does for humanity. And I think it is great that Swedes decide to have that be their big thing rather than something else. They choose with their national identity to associate man's or humanity's achievements in science. So what is pushing on the universe? Well, it turns out Albert Einstein's big mistake, where he invented this thing back in 1917 to keep the universe from expanding, it turns out it's exactly what we need. We need to have something that we like to call dark energy. pushing the universe apart. And if we use Einstein's ideas from 1917, it turns out that a detailed analysis means that we have to have a universe which is 30% pulling, 70% pushing. In other words, to explain our observations, we have to invent a new form of energy, which is 70% of everything there is in the universe. Turns out, and I don't have time to talk to you about it today, we also have to invent something called dark matter as well, to be part of that 30% that pulls. And in the end, we get this crazy idea that needs to be tested, because crazy ideas are only believable if you can predict new things and see if they're right. So we have to remember that research needs independent confirmation. You will have seen a couple weeks ago this great announcement of the detection of gravity waves left over from the Big Bang. This is a great result if true. It probably is true, but it needs a lot of scrutiny, and there is a chance it will not survive that. But that's the way science works, and science sometimes makes mistakes, but it's that process that has given us everything that we have today in modern society. So there are more than one way to solve most problems, and getting the same answer through a variety of techniques provides believability. And so the crazy universe that we predicted in 1998 was essentially this one, a 70-30 split between gravity that pulls or pushes and gravity that pulls. But you will note that only 5% of the universe are the atoms that make up the Earth and us and everything we can observe. 95% of the universe is stuff that we can only infer is there based on how the universe evolves over time. And most of you would rightly say, if you've got to make up 95% of the universe, clearly that means you just don't know what you're talking about. Well, probably not rightly to say that, because ultimately you're going to make predictions with this model and see if they come true. And since 1998, this crazy model has made prediction after prediction, every single one of which has come true to as well and as accurately as we can measure it. So in the same way Einstein's notion of a curved space was considered to be crazy, and the notions of quantum mechanics being crazy, they survive the test of time. And what is reality? Reality is the set of ideas that predict what we see in the universe. And our view of reality changes over time, and this is the current reality, and I suspect it will evolve over time. But in the same way Newton's laws are still useful today, I predict 100 years from now we may have a better understanding, like general relativity is to Newton's laws of gravity, but the same basic concept will remain more or less in place. So, results do not always have to make sense as a scientist. It is important to check your work, and most results give, science and research gives results in line with expectations. But research that isn't necessarily wrong. It can be the most exciting, even though more than likely than not, it's just a mistake. And one, as a scientist, needs to always remember this. So when I saw the result that said the speed of light may not be preserved because neutrinos seem to be going faster than the speed of light, I was very skeptical, but I was also very strongly of the view that we needed to test that result, not just assume it was wrong, but assume it needed to be tested with the highest level of urgency. And in that case, it was wrong, and that's not a failure of science. That is exactly what science is about. It's a celebration of science. And remember, you never know what might happen to you or your friends. Someone is going to make the discoveries. Someone was going to discover the accelerating universe eventually. And trust me, I never had designs of winning a Nobel Prize. I didn't even think I'd be able to become an astronomer. So someone is going to make these discoveries. And I will tell you that the discoveries are exciting, but it's the process of doing science that I find the most exciting, rather than the discoveries themselves. And discoveries are made by people in the right place at the right time, the right skills and passions to get things done. And they are people, especially now, just like people who are like you in the audience. They're no different. I'm not any different, and my friends that I grew up with are scratching their heads as much as I am the fact that I'm a Nobel Prize winner. So, risks. If you decide to do a career in research, you should be seeking to do cutting-edge research, especially if you're within a university. And most of us, I think, need to take risks to find our niche and then zero in on an area of pursuit. If it doesn't pan out by taking a risk, the worst thing that can happen to you is you'll need to get a less interesting job, which of course was the alternative in the first place if you decided not to do research. If you don't take risks, you're almost certainly guaranteeing the outcome that you will do a less interesting job. So our job is to go where no company and no other type of sensible person would go, to go out and explore the boundaries of knowledge. I always think you need to go with your gut feeling. I've always certainly gone with my gut feeling about what I think is interesting. I have never expected success, but I've always given it my best shot and see what happens. But I've always made sure I had a plan B in case my risk didn't come out. I don't want to, throw myself off a bridge. But I've always been willing to back my ability that something will happen that's interesting and acceptable in my future. I've always known that there's lots of interesting things to do in life. And the other thing you need to realize is everyone has bad days. And so you have to be positive to be successful no matter what life throws at you. Bad things happen to everyone, and you will be treated, for example, unfairly by your colleagues, your supervisors in your institution, and you will have bad luck. But in these cases, it's always in your interest to move on and forward with your career when this happens. Doing anything else sets you back and could result in the end of your career. And I should put one caveat. If you are truly being treated in a way which is unethical, then your institution will have ways to deal with it. And rather than make that justice your crusade, unless that's what your ultimate goal in life is, I suggest letting the processes deal with that in as fair and objective a way as possible. You need to have a life-career balance. Losing your life-career balance is something many people do in life who are successful. But I actually think it's not a necessity. I would say it's misguided. It's not what will ultimately make or break your career. I have worked too hard in my life, and that has probably set my career backwards rather than forwards. You need to work hard when you need to, but work normally when you do not. Being excited about what you're doing is far more effective at promoting your career than being scared about the future. I always like to tell people that you can choose to work 40 hours a week or 80 hours a week. Now, most people are not working at their best if they work 80 hours a week. I certainly don't. But talent is logarithmically spaced. The difference between you and your colleagues are probably factors of 2, 3, 5, 10, 20 in terms of raw talent. By doubling your life, your effort, you make up only a tiny bit of the difference between you and other people. It is not going to be the thing that ends up changing your life. Actually, being positive and having a life balance is going to be far better long-term and making sure you're happy. Because the goal in life is actually to be happy. It's not measured by your scientific successes. And so I encourage everyone to always do self-assessment and say, am I happy what I'm doing? If the answer is no, then change your life. Changing how you work, what you do, or even your career. And if the answer is yes, then I encourage you to keep challenging yourself, keep learning new things, and take risks, and remain happy. But don't be scared about change. Change is always good when it comes, and very scary when it's happening. So, for future prospects, for those who are in science or people thinking about doing science, just remember there is no shortage for positions for smart, capable people. Your current academic career, for those in your academia, is only one of range of interesting jobs you have in life. And if you work positively for success, knowing at some point a change or direction might be required, this change might be scary, but it can be exciting and rewarding too. So what's the future prospects of the universe? Nice little segue there, huh? Well, it seems to be dark energy. Dark energy is pushing the universe apart. And the more dark energy pushes the universe apart, the more dark energy holds the balance of power. In the future, instead of it being a 70-30 mix of dark energy versus stuff that pulls, It's going to be a 99.9999999% mixture of dark energy and the stuff like us that makes gravity pull. Because the universe is getting bigger and bigger, and nothing happens to us, but dark energy is part of space itself. So in the future, we can expect a universe that is going to continue to expand at an ever-increasing rate. And unless this dark energy disappears, this universe will expand faster and faster, and eventually the objects that we see now will be so far away that light will not be able to travel to us from them, because space will be created faster than light can travel through it. A universe in which there are no galaxies to look at. A universe where I will almost certainly be unemployed. Thank you.